When Albert Einstein famously said, "God does not play dice with the universe," he wasn't objecting to the idea that randomness exists in our everyday lives. If I roll this die, there's an equal chance of it showing up 1, 2, 3, 4, 5, or 6. Even though we could, in principle, measure everything carefully enough to completely determine its motion, effectively, in practical terms, it's a random event. What Einstein was objecting to is not this kind of randomness arising from complexity or chaos. What he didn't like was the idea that randomness is so essential to the laws of physics, so built into their structure, that even with the most precise measurements and carefully controlled experiments, there will always be some level at which the outcome is, effectively, an educated guess. Let's play some dice with the universe and talk about why. If I have a regular die, it obeys the laws of classical mechanics. I can hold the die, throw it, and watch it tumble and land on one side. Everything the die does is determined by the throw, the environment, and the surface it lands on. But what if we had a die that obeyed the rules of quantum mechanics? Uncertainty would be built in. We have a starting point, the die in my hand, and an outcome, the die on the table showing a result. After we throw the die, but before we observe the outcome, the quantum die is in a superposition of all the possible results, a kind of ghostly combination of all 6 options. Just like with the famous Schrödinger's cat experiment, it's not until we look at the die that we know which of those results will become real. It may seem extravagant to suggest a superposition instead of just not knowing what's happening. But when scientists do experiments with particles, they find that the way they act between the starting point and the final result doesn't make sense if the result is predetermined. Our experiments tell us that a particle moving through space acts as though it's spread out across every possible path, only settling on one when it's finally observed. Physicists use a mathematical tool called a wave function to keep track of a particle when it's not being actively measured. The wave function is just a set of numbers assigned to each possibility for the particle: its location, its speed, its spin, and so on. Those numbers determine the probability of each specific outcome when you actually make the observation. How does a particle go from being a wave function, a superposition of existing everywhere at once, to being observed in just one spot? That's a really good question that physicists have debated for over a century. Does the wave function collapse at one spot? Is there some hidden information that tells it how? Or maybe the particle is actually in all those different places. In this scenario, called the many worlds interpretation, different versions of our universe branch off every time a quantum event happens, and the measurement is just our way of figuring out which universe we're in. In the case of the quantum die, the wave function tells us that the probability for each result is 1 in 6. And when we do the measurement, there's a 1 in 6 chance that the wave function will collapse with 3 showing on the die. Now, if we roll 2 quantum dice, each die is still in a superposition of every possible state until we measure it. But the mix contains more states in which the dice roll comes up 7 than any other number, so there's a higher probability on the number 7 than 6 or 5 or 4. While you'd expect the same distribution on average with classical dice, in the quantum case, it's because all of those results are actually happening until you look. When particle physicists do experiments, they have to account for every possible outcome and the weight each one has in the wave function in order to predict the result. It's impossible to make a prediction with absolute certainty, but if we do an experiment many times, like rolling dice over and over, we can say with incredible precision what the distribution of results will look like.
When it comes to quantum theory, we have the qualitative and the quantitative predictions, but we don't have a good description of the underlying reality. And this is why there's still a plethora of interpretations going on in quantum theory, because quantum theory was not created historically from a belief in an interpretation about the world. It was sort of first comes the math, and now we're filling in our description as to what the math is telling us after the fact. And so we have interpretations like many worlds. We have interpretations like wave function collapse. It's not clear that any experiment can really distinguish any of the interpretations if all of the interpretations are consistent with the same theory. The theory is what tells us if we go to the lab and do something, what should we expect to see?
At some level, everything is quantum, big and small, and everything we observe is determined by probabilities. While we can't say whether those probabilities arise from the sudden collapse of a wave function or the continuous branching off of new universes, we do know how to calculate them. Quantum mechanics says we do have to play dice, but at least we know the odds. And thanks to superposition, at the quantum level, everyone's a winner.